And what I want to do is I'm going to generate some data. So this is going to look a little bit different than what we generated at like 9 o'clock this morning. So to walk through this, we're going to make sure that we get the same results by setting a random seed of 42. We want to make sure that we all generate the same pseudo-random numbers here. So I'm setting a random seed of 42. I'm generating data, so I'm generating age, I'm generating whether or not people are partnered, I'm generating how many children people have, and generating income. So what I'm going to do is I'm fitting a model here or I'm creating a data set where I believe that income is linearly related to age, to whether or not people are partnered, and whether or not people have children here with some additional error as well. I totally made this up. This is not based on real data, but what I have here is that income has a y-intercept of 15,000. The slope associated with age is 750. If people are partnered, on average, their household makes an additional $20,000. And for every additional child that family has, their income is reduced by $2,500. I have no idea if this is anywhere close to correct. I literally just made these up. I also used a list comprehension here to show that income was going to be positive or non-zero. Wanted to make sure that income was at least 0 and not negative. We're going to combine our results into one data frame, and then we check out the first 5 values here in that data set to make sure that we did this properly. We get our data set here. There should be 100 values in it, but I'm just checking out the first 5. We have age here, we have whether or not people are partnered, how many children each couple has, and what is the household income here. Obviously the household income is generated values from a normal distribution, so this goes out way more precisely than actual income would be. Actual income should truncate after 2 decimal places, but it's not really going to matter for us here. If you run this cell, this is a cell that's going to allow us to create columns of missingness. So specifically, we're going to be able to create a column that is missing completely at random. Missing completely at random is like that coin flip or that Petri dish randomness, where there's nothing special about those Petri dishes that I'm missing, I just happen to miss those. Also got a column for missing at random. So in this case, my data are missing at random. So that was the sensor that was knocked out for a period of time. Once I put time into my model, that could account for the missingness. And then missing not at random. So if my data are missing not at random, then in this case, I'm going to saying that, like, for example, income, like the value of income influences whether or not income is missing itself. So as income gets lower or gets higher, that changes the probability that somebody responded to the question about income. So go ahead and run that cell as well. And what I'm going to do is I'm going to generate some missing data. So I'm going to generate 3 new columns. One is called age missingness, one is partnered missingness, one is income missingness. Age missingness, that is going to be missing completely at random, and I'm going to set 30% of those observations to be missing. I'm going to say that partnered missingness will be missing at random, and it's going to depend on age. So as age increases, you are less likely to respond to the question about whether or not you're partnered. And then income missingness. I'm going to say this is not missing at random or missing not at random. And in this case, I'm going to say that as your age increases, you will be less likely to respond to the question. And I'm going to set your probability of missingness here to be 20%. So 20% of those observations should be missing. To look at what this looks like in our data frame, there's a specific reason that I've done this. I have not made my data in my first 4 columns missing yet. Instead, what I've done is I've just created a new column for each of those missingness values. They're like missingness indicators. They're going to take on values of 0 and 1. We're going to have a value of 0 if that data is observed, and it will take on a value of 1 if that data is missing. So for example, partnered missingness here takes on a value of 1. That means that theoretically what we're saying is that this value of partnered here is going to be missing. I've written code to allow us to create a data frame where that actually is applied. So here we have children, age, partnered, and income, where some of these have now been set to NAs, or in this case NANs for not a number, where those have been set to missing. Yeah?
You could just sample a list with NAN and the actual value, probably do whatever. You could directly sample it.
Correct, but what I wanted to do is I built out functions to be able to do this for a couple of different reasons. Down below, what we're going to do is we're going to be able to visualize this and look at what the observed versus imputed values look like. And so having those missingness indicators are helpful there. So what I'd like for us to do is visualize our missing data. I'm going to go through 3 quick examples from the Missing No package. I find one of these to be exceptionally helpful. I find 2 of these to be less helpful, but you may find them to be more helpful. So I'm going to import here, or I'm going to run msno for missing no dot matrix of df missing. So this is going to take in that data where some of it's missing, and I want to be able to visualize that. What this package does is this is going to show me what values are observed and what values are missing. And this is convenient because now I can see that all of children is observed. There's no missingness in there. I can see that age and partnered and income are also missing with various patterns here, but it allows me to visualize my data frame and see how these values are missing from one another, which I think is relatively cool. I think it's good to be able to quickly visualize that. Obviously, this is going to be cumbersome if you're dealing with 100 columns in your data, but if you're dealing with 4, it does a decent job. You can also use a heat map and a dendrogram to, or these are 2 of the other methods that I saw in the Missing No package. Heat map and a dendrogram will allow you to visualize sort of the relationship between what values are missing together. And so msno.heatmap allows you to check this out, and msno.dendrogram. So dendrogram, like a clustering diagram, this tree-based diagram will allow you to see how these are missing related to one another. In terms of this, it's a little weird because for trying to remember what exactly, for most of these are going to be missing independent of one another. Like one of them, I can't remember which one was missing just completely at random. There was nothing special about it. And another one, it was missing based on itself. Income was missing based on itself. So this is not wholly informative here, but as you're trying to look at the data that you have in the future and you think, oh, does missingness here correspond with missingness in other columns, especially when that missingness is correlated, or you think it might be, this dendrogram might be helpful in being able to visualize which things are most correlated in terms of what's observed versus what's missing.
What is the meaning of the y-axis numbers? Just explain.
So the y-axis, I believe it's just a measure of like similarity or dissimilarity. I don't think there's a real tangible like takeaway of what that is. It's not like 5 values in common versus 4 values in common. But the way we would measure like the distance from age to all of these other ones is a distance of 6. We would say that income is about 5 units away from children and partnered, and children and partnered are like 4 units away from one another. But again, those units don't really mean anything in context of how much data we have. It's more of, it's a measure of similarity to say like which missingness, like the correlation among the missing values that exist there. That's a
correlation. It's like a correlation plot in a sense.
Yes. Maybe it was recently like teaching hierarchical clustering, and so my mind is in that mode, and I'm thinking about this in that way. But it might just be the correlation. I can't say that with certainty though.
It's only the diagonal. If you drew a correlation plot, you would see all 4 times 4.
True.
Here you only see closeness.
True.
Might be better to show the full correlation plot.
Yeah. So Missing No has a number of ways to visualize this, and it's going to depend on kind of what your background is and what you're interested in, what you're interested in showing and studying. For my money, I think that this is the best thing to look at. But depending on how you get into this or what you want to show, there might be other things that are better for you.
I mean, I'd say people usually do this on calculus, like the exploratory data analysis of the data sets, the first thing to do.
Sure.
If you look at the correlation plot, you get an instant feel for is it missing not random, utterly not random, or it's very determinate. If you see glowing, huge correlations like 6 and
Right. And so
age and income.
right. And so looking at that is going to be helpful in determining, the like missing at random especially. Is one missing, and does that cause something else to be missing? Sometimes we might have to go deeper though to see if it's like a certain value of one that influences whether or not something else is missing. Maybe, for example, somebody's less likely to respond to a question about income based on their age. People who are older might be more likely or less likely to respond. And so looking at that correlation matrix, I don't think that in and of itself wouldn't tell that problem, or wouldn't solve that problem for you.
Sure. I'm just trying to say that the n-prime isn't very useful because the y-axis is totally arbitrary and you can't correlate it to anything else. You don't know it's the correlation 0.99 or 0.01.
Yeah.
It's just whack.
Yeah. So again, you may find different uses for each of these things. You might find them to be more useful or less useful depending on what it is you want to do. So I've got some code here to generate histograms, and what we're going to do is we're going to look at histograms top to bottom. Specifically, go ahead and run this cell. What I'm going to do is I'm going to look at the actual original histogram of our data, and then I'm going to look at mean, median, and mode imputation with that data, and I'm going to see how does this change. So if we impute the mean or the median or the mode, how does that histogram change based on this? So once you've run that, then we should be able to examine a few different imputation methods. So the first thing I have here is mean imputation. So this function here will take in a data frame, take in the column that you want to impute, and take in that missingness indicator column. And it's going to go through and say, let me look at that column, and if the column is there, or if that value is there, we're just going to keep that in. But if that missingness indicator takes on a value of 1, then what I'm going to do is I'm going to fill in the mean of that column. So this code will do exactly that. This cell is going to create that new column. So I've got a column called age mean imputed, where I've imputed the mean of age for any missing value. And let's compare these histograms. So let me try and zoom in a bit. So what we have up top, this is the real histogram of age. So we're looking at age. It ranges entirely uniformly from 20 to 60. It was randomly generated. As we look down below, though, we have the observed and the imputed histogram. So what we have here is the blue values here are what we observed in our data. And then the orange values here are the imputed values in our data. So in this case, if I remember correctly, it was either 20 or 30, but I think it was 30% of our values for age were set to be equal to missing. Because of that, if I filled in my missing values here, all with the same value of mean, what that's going to do is it's going to dramatically distort my histogram. And this is not going to be a good thing for us, because if we have 20 or 30 or 40 or 50% of our observations that are missing, this is just going to go up and up and up. Yes?
But if you bin it in like 5-year intervals, will you see much difference?
What do you mean if we bin it in 5-year intervals?
You show the histogram of age binned by 5-year intervals to see shape distribution, which might or might not.
So how would that, so yes, obviously if you change the bins, that changes what the shape of the distribution looks like. But if you're doing mean imputation, that you're still going to see an enormous spike in the middle here, whether you're doing this bin by 5 or, I think in this case, it's been by like 3-year intervals or something like that. And kind of the point of this is to illustrate that by imputing the mean, we're going to dramatically distort that histogram or distort the distribution of our data. Thinking from a statistical significance point of view, what's the problem with this? What are we going to run into with this if we're trying to calculate statistical significance, like the effect of age on
Variance
something?
becomes meaningless.
Yeah, your variance and your standard deviation become meaningless. So if you think about the formula for standard deviation, what I've got here is that formula. So the sample standard deviation S is given by xi minus x bar squared, so each observation minus the sample mean squared. You sum that up, divide it by n minus 1, and take the square root of that quantity. So that is the sample standard deviation formula. If I were to, let's say that just without loss of generality, I've kind of ranked, or I've sorted my column, and all of my observed values are 1 through k, and then my missing values are k plus 1 down through n, the last part of my column. Well, if I'm going to impute the mean for k plus 1 through n, for however many missing values I have, now I can rewrite my sample standard deviation calculation like this, where nothing has really changed. I've just said I plus 1 to k plus I equals k plus 1 up to n. So I've just taken that summation and broken it out into 2 pieces. This piece reflects my original data, or the actual data that I've observed. But in this situation, if I've imputed the mean everywhere, what I'm doing is I'm now taking the mean minus the mean, which is 0, squared, which is 0, summing that up, which is 0. So ultimately, what I've done is the numerator, for my sample standard deviation, my numerator stays fixed. I haven't made any changes to that numerator, but this denominator has increased because now my observed sample size is much larger. It might be inflated by 30%. And so in doing so, my sample standard deviation is now going to be underestimated, or my variance is going to be underestimated. Well, anytime I want to generate a confidence interval, or anytime I want to do a hypothesis test, or anytime I want to calculate a regression coefficient, the standard error of a regression coefficient, I need to rely on my sample standard deviation, or my sample variance. But, as you mentioned, that is now dramatically underestimated. It's essentially meaningless. And so what that does is if I did generate a confidence interval for the mean, any confidence interval that relies on that mean is now going to be narrower than it should. But that confidence level doesn't change. So we're still 95% confident that the true mean is in between these numbers, but we've just made that confidence interval smaller. So that means that things look significant when, in actuality, they probably aren't significant. Yeah?
What if you just store the standard deviation before you do the imputation and use it instead of using the actual?
So it's still going to be underestimated because you just have fewer data points that you're looking at that mass between, or you're looking at the spread between those points. You could try and do that and just say, let's look at this and essentially keep n to be that pre, whatever sample size. But that's like before imputation.
No, I'm saying before imputation. Before imputation, ignore everything which is missing. So ignore rows or whatever variable is missing.
Right.
Just store the standard deviation as the rows square in your target variables present.
Yeah. So
in that case, shouldn't that give you a reasonably accurate estimate for?
It would not, because now we're taking the standard deviation of n1 observed values, but the true population standard deviation should be based on n2 observed values, where those sample sizes are going to be different because n1 is going to be based on just what's observed. And depending on how your data are missing, if your data, for example, are missing not at random, then in that case, your standard deviation for your income that you've observed probably doesn't do a good job of explaining the spread of the incomes for people that are unobserved.
Missing at random, and if you took the standard deviation of the smaller sample, it should still be a reasonable estimate. If they're missing not at random, it's not.
Right. And so, if they're missing not at random, which is more common, it would not be a reasonable estimator. I also think that there would be additional corrections that you would have to make. I don't think that you could just take the sample standard deviation of your first k observations here and divide it by k minus 1 instead of n minus 1, and at that point just essentially plug that in. I'm sure that there's some estimation that's going to be off there, but I can't say right now like what exactly that's going to be or what direction it might be skewed in. I mean, I think that it would be a better estimator certainly than just using this sample standard deviation, because of course we know this is going to be underestimated, but I don't know the behavior of that estimator and how that, if it would have higher variance or whatever relative to what it should be. So we can also do the same if we want to visualize median and mode imputation. So a common, if people say, oh, mean imputation might not make sense, we should do median imputation as well, because it's just robust to outliers. And if we do median imputation, then we're plugging in the median for this and not the mean, so we're still contributing to this. Well, we're still plugging in a missing value for this, or one value for this, and we're still going to underestimate our standard deviation. We can look at this, and we're still, in this case, I randomly sample these observations from a uniform distribution, so unsurprisingly, the mean and the median are right about the same spot, but we still see that we're still distorting the histogram substantially here. If we were to do mode imputation, which we could do with quantitative or qualitative features, we could try that. But if we were to do mode imputation, things might look a little bit different than we expect. In this case, when the mode happens to be down here closer to 30, then we'll notice that our observed and imputed mean goes pretty far over to toward that mode. So we're not guaranteed to necessarily get good estimates for this. So in short, and we could calculate the standard deviation of these imputed values, but in short, what's going to happen is that this is going to be an invalid method of imputation, because what we're doing is we're just making up data. We're just plugging in the mean everywhere, or the median, or the mode everywhere. So while it seems like a clever thing to do, it's something that we want to shy away from, whether our goal is to do prediction or to do inference. The next thing that I want to do is chat really quickly about regression imputation. So for any NA value in a given column, let's build a regression model for that and fit a regression model to that. Because then it feels like we're not really going to distort our histogram nearly as much, because now we can spread our values out. We're not just imputing one, but instead we're basically predicting a range of values. So to explicitly walk through this, let's say that I have an observation where income is missing, but let's say that age and sex are not missing. What I would do is I would basically take all of my data where income, age, and sex are not missing. You could think of this as your training data set, looking at age, income, and sex. And I build a model where income is linearly related to age and sex. Estimate beta naught hat, beta 1 hat, and beta 2 hat for that. And then what I'm going to do is, once I've built that model, I'm going to then say, let's plug in the value of sex and age where income is missing, and then make a prediction for income and plug that prediction in for income. The upside is that it's going to be an improvement over doing mean imputation. It is going to do a better job of estimating the variance or the variability of the data. And it's also easy to comprehend. We can say logically, this makes sense. The downside is that it's still going to distort our histogram, it's still going to underestimate our variance, and it's still going to be an invalid method of imputation. So the last thing that I want to show you in the code is this. So down below, I have a function for regression imputation, and what you will do is, if you want to do this, you can pass in your data frame, what you want to impute from. You can pass in the column of the imputation, what column you want to impute. Your X columns, basically the things you've observed that you want to use in order to predict income or whatever your Y variable is. Your missingness column, what is the name of that column that's, or the indicator of the missingness. And then the type of regression. I built this function out to handle linear regression or logistic regression. So if you're trying to predict a continuous outcome, you might use linear regression. If you want to use, if you want to predict a binary outcome, like partnered, for example here, maybe you do logistic regression. You could do this beyond that. You could use a random forest, or you could do Poisson regression or something else if you wanted to get fancier with this. This is not limited to linear models or just linear regression, but I think for ease, I'm just going to talk about it like it's linear regression. And you could use a different model if you wanted to impute this. So this is only, the way that this is run right now, this is only set up to do linear or logistic regression.
This is assuming a normal distribution.
This would be assuming, yes. So any assumptions that you would make in your model would be assumed for this. So I would be making the assumption that the errors would be normally distributed, much like we assume that our errors are normally distributed anytime we want to construct a linear regression model. Exactly.
Right.
So you're making that assumption, which may not be valid.
Yeah, if it's not, you can see a priori, it's not normal distribution like age. Age is going to be negative exponential. You can do a Box-Cox transform before you do the regression.
Yes. So with this, as we talk about, as I talk about these methods here, yes, there are many, many extensions that you could apply to these methods. What I want to get at is, as we think about applying these methods, I want to walk through why the methods are right or why the methods are wrong, and identify like what are those pitfalls that we want to identify. Specifically, if we think pragmatically about us using this in a business setting, it is, depending on the amount of time you have, depending on the amount of sway you have over this kind of data cleaning or data collection process, there may be, at least for some of you, some limitations to what you're able to do. And the reason that I like walking through this, because as we're going to see, regression imputation itself is still invalid, or as I mentioned. The problem is that in many situations, you might not be able to do the, quote, right way, whether it's due to time or computational limitations or whatever. You may not be able to do that proper way of imputation. So what I want to do is I want to walk through this to show you what are the different things that you can do, and essentially try and, to use a sports metaphor, like move the ball forward as much as you can. As you go into your workplace, say, oh, we're just dropping our observations. Let's try instead doing mean imputation, but let's try using regression imputation or something like that. Recognizing that, I will fully recognize and admit here that what this has is not necessarily going to be like, this regression model by itself will not necessarily be able to be applied to every possible situation that you could come up with. So with regression imputation, if you have defined that function, what I want to do now is we can create a column in our data frame where we use regression imputation. Here, I'm using children, partnered, and income in order to predict age. So I'm fitting a linear regression model based on where I've observed all 4 of these, fitting a model on that. Then I'm using that to fitting a model on these 3 values as my x, or these 3 variables as my x, in order to predict age. So if I want to compare my histograms, I've got my real histogram here. And now when I look at the observed and imputed histogram, I still do have I'm doing better. I'm not just imputing one value, I'm imputing a range of values. But if we wanted to look at the standard deviations between these, we're going to notice that the standard deviation of our real data is going to be significantly different from the standard deviation of this observed and imputed data. So I have 2 lines of code here to show that. If you look at the sample standard deviation of the imputed regression column, that sample standard deviation here is 10.15. The sample standard deviation of the true column here is 11.9. So going from the true sample standard deviation of about 12 to the sample standard deviation of about 10, that's a pretty dramatic difference. And so even though regression imputation sounds like it would be really, really close to the true value, in this case, it still quite isn't. There's a couple of additional cells down here as a work in progress for additional things that I've been working on, but those are not done yet. So if you were to run those, you will get errors because I did not do this. So you're welcome to take a look at those if you want. Essentially, what I wanted to do was generate scatter plots that we're actually going to see together now. So I'm going to move back over to the slides. And as we do regression imputation, like we've got here, it's an improvement over mean imputation or median or mode, and it's easy to comprehend, but it's still going to be an invalid method because we're going to underestimate our variance or our standard deviation in our data. And so visually, this is what that sort of looks like. So this is an image that was taken from Andrew Gelman and Jennifer Hill's book, Data Analysis Using Regression and Multi-Level/Hierarchical Models. But what we have here on the left-hand side is a deterministic regression imputation. So as we look at our data, we have a bunch of values here in dark black dots. Those are the values that we would impute using a deterministic regression imputation. That is, whatever the predicted value is, that's what we generate. However, the next step for us is not to do a regression imputation, but instead do a stochastic regression imputation. What I mean by that is basically generate a line of best fit or some model that will allow you to fit to the data and make some prediction. But when you make that prediction, don't just make the prediction for that line of best fit. Instead, consider adding some random error to this, error that might be estimated from your data. So if you add an error to this, now you can essentially add a random error to each imputed observation. Now, the scatter of your data tends to be more like what we would expect to see. And that distribution, that scatter plot here, looks better than this scatter plot here. Because obviously this is going to underestimate our variance. We can visually see that without even calculating variance. But over on the right-hand side, the imputed values in dark black dots look much better and much more like the lighter gray dots of the actual observed values. So to walk through what stochastic regression imputation is that for any NA that you have for a given column, you're going to replace NA with a value predicted from a regression line or from any model. Again, I'm going to default to a linear regression model here just because I think it's easiest to talk about it in that sense. So what you would do is you would estimate beta naught, beta naught hat, beta 1 hat, and beta 2 hat using age and sex to predict income. But what you would also do is look at the standard error of those predictions, that standard error of those, the standard deviation of those predictions, and you would then randomly generate an error from a normal distribution with a mean of 0 and a standard deviation of that estimated standard deviation. You're going to use that to basically come up with a prediction and add some random component or some stochastic component to that data. So let's say that I were to predict a value of income, I predicted $50,000. Well, then I'm going to randomly pull an error from a normal distribution, and maybe that adds $5,000. So instead of predicting 50,000, which would be right on the line of best fit, I actually generate a value of 55,000. So this is an improvement over regression imputation, and it's going to allow for better estimation of the true variance. It's going to get us closer to properly estimating the variance in our data. But it still does underestimate our variance, and it still is an invalid method of imputation. Steve?
Yeah, so does this only work for lines where you have income, age, and sex? So if there's any missing, if you have a large number missing, this will break down.
So you would have to generate a model based on where you have observed income and age and sex. Yes. So that's not saying that you have all values of income and age and sex observed. And in fact, in this case, income is that thing that you're trying to impute. So you know income's going to be missing. However, when you are fitting your model, and you can think about this like the training set, what you're doing is you're fitting a model where you've observed income and age and sex. If, for some reason, you only have 5 observations in that group or something like that, then you're going to run into an issue, because then obviously this model is fit on only 5 observations. Yeah, so we are absolutely, like, any model we fit here is certainly going to be limited by sample size, just like for any other model that we would want to fit. One related note to this, so taking a slight deviation from stochastic regression imputation, or kind of this direction we've talked about so far, what I want to do is I want to move on to something called hot deck imputation. So hot deck imputation is where we take our observations and we split them into strata. So maybe I split them up based on age and sex, and for any NA value in a given class, I'm going to replace that NA with a random observed value from that class. This is like bootstrapping. So I've got an NA value, or in this example here, I've got 23 different values. I've got 20 observed values and 3 missing values for income, for example, among 18 to 34-year-old women. So I've observed age, I've observed sex, and among these, and I split them into groups, and I'm looking at 18 to 34-year-old women, for example. In this case, I've got 23 observations. 20 of those values, I've seen sex, or I've seen income. 3 of those values, I have not seen income. The way I fill in those 3 missing values is I bootstrap those 20 observed values. I sample with replacement from that group of 20 observed values and just fill it in for my missing value. Yeah.
Is this synthetic data generation, or is it?
It is not synthetic data generation. So this is not using like SMOTE or anything like that. This is just actually using the real data that you have observed. And the reason that it's called hot deck imputation harkens back to when you would like pass cards into computers in order to make programs and things run. And with that, if you were dealing with the deck of cards that were like passed in or actively being passed into a computer at a given moment, when the decks came out, they were still warm. So hot deck imputation corresponds to this when we're dealing with data that is currently being processed, like from our current data set. There's a cousin of hot deck imputation called cold deck imputation that does the exact same thing, except you're dealing with like a separate data set. So rather than finding other 18 to 34-year-old women from our data set, we're going to like another data set to find 18 to 34-year-old women and imputing those values. And I do not believe I've read any advantages of cold deck imputation over hot deck imputation, because there's a lot of issues if you're gathering data from a different population or a different point in time or whatever. It just gets much harder to deal with that. So in just about all cases, hot deck imputation tends to be preferred.
How is the cold deck different?
The cold deck imputation is that rather than bootstrapping from your actual, like the data that you've read in and that you're currently working with, the cold deck imputation is where when you're bootstrapping to fill in those missing values, you don't bootstrap from the 20 observed values in your current data set. You basically have like another set of data that exists from like some other research project or whatever that you might sample those from.
So we're assuming the distribution of 2 is the same?
Correct.
So let's say taking ages from the American Community Survey.
Correct. Which is why in general cold deck imputation is not something that people do. That's why I only have hot deck here in the deck. Because with that, hot deck imputation is much easier. You don't run that risk of making those assumptions, and you don't need an extra data set like on deck. I promise I will stop saying deck. But hot deck imputation just tends to be better overall than cold deck imputation. So The upside to this is that you're using existing data. The downside is that if you impute columns separately, you're going to ruin any multivariate relationships that you have. So let's say that in this case, I'm predicting income. Let's say I also use this to predict another variable that we had, like partner. Well, if I'm using this to predict income, and then I'm also using this to predict partner, and if I impute these values separately, like I do it first on income, then I randomly get new values for partner, what ends up happening is that with this, the correlation between our different columns might now be ruined because I'm randomly filling in like different values from different observations, which is not something that we necessarily would want to do. So in that case, you would hopefully impute columns jointly. So if you were trying to predict income, or you wanted to impute income and partner, you would just grab one observation or one value and fill both of that observation's values in for that missing value. So hot deck imputation is more outmoded. It's something that you will see a little bit, and you can show that it's similar to regression imputation, but not. It's like when you break things down into categories, but generally we use regression imputation or a cousin of regression imputation. Yeah.
So if you did that jointly, would you override existing data and one of the columns is missing?
So you have to get into that as the data scientist. Would you override it? Like, let's say that you had one row in your data set, you're just missing income. And then another row in your data set, you're missing income and partner. If you're going to bootstrap values and you're going to say, okay, I want to bootstrap and pick somebody where I've observed both income and partnered already, and I want to basically impute that for this, am I going to impute income and partnered for both of those missing observations? Am I just going to do impute, or am I just going to impute it for the one that's missing both of those? Then use a different value for the next one. Like it's a decision that you have to make. In general, I am never in favor of overwriting existing data because you know, or you have higher belief that that data is true. So I would never personally override data, but that's up to you.
So potentially you could just impute with values where only those specific columns are missing.
Correct, and that gets to the pattern submodel method, which we're going to talk about in a moment. But yes, that's a good question. Yeah.
Say in a column we have like say 60% of the data is missing.
Yeah.
So would you still impute that, or would you drop the column?
Yeah, so that's a really tricky question to answer. The question was, if you have a column where 60% of the data are missing, do you impute it? And there's not a good answer to that. Obviously, imputation methods are going to have their limits. You're going to be limited by the data and the information that you have. And that, I can imagine, is probably the only situation in which we might use something like cold deck imputation, where we just don't have enough data in our existing data set in order to use the current data that we have. In general, I don't think that imputation is very successful when you have 60, 70, 80, 90% of data that are missing. Especially if the reason that they're missing is like they're missing not at random or they are missing at random. If they're missing completely at random, then it's better, but it's still very dicey to do. But I am not willing to say like at that point like you must drop it or you should drop it or whatever, because maybe that's the data you're trying to predict. Maybe that's your Y variable, and if that's your Y variable and the target that you want to predict, in that case, you probably wouldn't want to drop it. Or if it's the most valid predictor of what you have. And I think that the pattern submodel method will get around that issue where you're missing 60% of a specific feature. And we'll talk about that in a moment. Yeah?
Looking at the clock
I'll
and
step
the
over here.
preciousness of your class, might I ask you to spend a few minutes on missing data when you're doing data cleaning? In some ways analogous, in some ways very different.
Yes. So we, in the practical recommendations, and we'll get to this in probably 10 minutes.
For non-census type data, for non-questionnaire type data. And maybe this is some lessons we can carry to other categories of data.
Yeah, certainly. Let's push through this. We'll wrap this, like the different imputation methods, up in probably 10 or 15 minutes. We'll get into those practical considerations and we can move more into like a Q&A at that point. So this gets into like the intuition of imputation. So like, what is it? So let's say here, and I want to ask this of you. let's say that I have 10,000 observations, and I have literally observed age for everybody, and I have observed income for everybody. I've observed sex for 9,999 of those people. 20% of my observations are male, and 80% of the observed values that I have are female. What should I do? If you were in this situation in general, I'd say, what would you do? So what would that be? If you have this situation where you're literally missing one observed or one value here.
Remove that row.
Okay, remove that row is practically what we're probably going to do, because in that case we're like, let's remove it. It's not worth our time to try anything else. So practically, that's what we're going to do. Let's say that that's not allowed in this one case, just for the purpose of this. Generally, that's what we would do. But what would you then try and do? What would you fill in for that value?
The distribution of income condition for male and female, and try to further is there.
Yeah, so I heard a couple of murmurs from the audience that we might put in female. So if we put in female, that's not something that we can validly do, because at that point I'm saying that I'm certain that this value is female. By making up that data, I'm saying I'm certain that this value is female. Well, I can't do that, or I shouldn't do that, because now I'm just making up data and I'm subsuming my understanding and my judgment, which is clouded judgment at best, in for this. So that's probably not something that I'd want to do. Whenever I ask my students this, they look at me kind of funnily and they're like, well, wait, do we fill in male? And I'm like, well, no, because if we fill in female, like we're making up that data. If we fill in male, we're still making up that data, and we're now giving it a substantially less likely value based on this. So then someone might say, well, let's do as you suggested. Let's build out a distribution for this, and let's say, all right, let's look at income and age, use that to try and predict sex and see based on the observed data that we have, what is the probability that this value should be male or female? And if it's, if female is sufficiently high or if male is sufficiently high, maybe we plug that value in. But we don't want to do that either, even if we add a random error to it, because what we're doing is we're still making up data. So I want to impress this point upon you. Anytime we take data and we plug in one value for that data, we are making up data. No matter whether we use a model to predict it or we just use the mean to predict it, we're making that data up. So that is something that we cannot do, or I'll say that's something that we should not do. So usually we guess, fill in female, but we're making up data. Do we fill in male? No, because we're making up data and it's probably a less likely value. Maybe we use income and age to predict sex and fill in the likeliest value. Maybe we add a random error to it, like the stochastic regression imputation. But at that point, we're still making up data. So optimally, what we would do is I would love to replace this NA with a distribution. I would love to be able to get rid of that NA, and I want to put in a Bernoulli distribution in here. A Bernoulli distribution is a value that takes on two outcomes, 0 and 1, and it has a constant probability of success. So what I'd like to do in this particular instance is maybe I want to fill in a binomial distribution with an 80% chance of female and a 20% chance of male. Or I might fill in a multinomial distribution for this. So let's say I've got male, I've got female, and then I've got a third category here. So I might try and fit a distribution to this. That distribution would be the set of all values that sex can take on, in this case, and how frequently we would observe these values. So it's just going to be like a little bar chart. The downside to this is that, the upside is that the distribution is going to totally summarize our uncertainty or our certainty in this. So if we say, look, I'm really not certain, maybe it's 50-50, or if based on our age and our income, I say, look, the chance that it's female is 95%, the chance that it's male is 5% based on the data I've observed, that distribution totally summarizes our uncertainty. The downside is that we can't, in Python or in Pandas, plug in a bar chart in there and say, all right, now do data science, which is what we would like to do. So instead, what we have to do is we have to kind of pretend like we've done that. And that's where we get into imputation, or specifically the proper way of doing imputation. So what I'm going to do is, if I can't put a distribution in here directly, what might I do instead? If I can't put a full distribution in here, what can I do instead?
where you might say, gee, I'm gonna rerun the calculator. The human part takes many, many days. The computer part often takes minutes. Might say, gee, I'll rerun it, say 10 or 100 times, and I'll fill in different runs with different possibilities in proportion to the distribution.
Yep, that's exactly what we're going to do. That is the proper way to do imputation. Because at this point, what we're doing is we're not making up any data.
Simulation already.
We are simulating. We are summarizing our uncertainty or our certainty in this missing value with a distribution. I'm going to basically create like 10 different copies of my data set, or if you've got more computing time and more money and all of that, 100 or 1,000 or 1,000,000 or whatever. But what I'm going to do is I'm just going to stick with 10 for now. I'm going to create 10 different copies of this data set with NA in it. And since I can't put in that distribution directly into each of those, I'm going to sample from that distribution. So by sampling from that distribution, what I get to do is, let's say that it was 95 and 5, 95% chance of female, 5% chance of male. With this, what I would expect is that on average, about 9 of those data sets would probably contain female, one of those data sets would probably contain male. Then what I would do is I now have 10 complete data sets where I've observed age, sex, and income for everybody. Then what I'm going to do is I'm going to do my final analysis on each of those 10 data sets. So let's say my goal is to build a model predicting income based on age and sex. Now I can do that. So I can build a linear regression model on data set 1 and look at what that model looks like. I can fit that model on data set 2, on data set 3, all the way through data set 10, and see what each of those 10 models look like. If my goal is to generate predictions or predicted values, what I can do is literally take my test set or whatever observations I have, generate those predictions on each of my 10 sets or my 10 models, and then average those predictions together. Where for that first test observation, I come up with an income prediction on data set 1 all the way through 10. I now have 10 different predictions for that person's income. I average those predictions. Now that is my one prediction for that one test observation, but it's based on these different data sets that allows us to summarize or simulate our uncertainty there. Now, in this particular case, those numbers probably aren't going to be very different at all, or in most cases they might be identical, because if 9 out of those 10 data sets happen to have female plugged in there, then all of those models I would expect to be exactly the same. However, this situation is not realistic. In general, you're going to have NAs all over the place. Because you have NAs all over the place, you're going to have like many distributions all over the place. So a lot of these values are going to be randomly simulated, and a lot of these values are going to differ from one data set to the next. So your linear regression model, or your logistic regression model, or your random forest, or your neural network, or whatever it is you're trying to fit, is going to look different on data set 1, 2, all the way through 10. And so if your goal is to generate predictions, you're going to generate predictions across all 10 of your data sets, and then aggregate those predictions together, much like a random forest aggregates predictions from each of its decision trees. If it's a regression problem, average those values together. If it's a classification problem, you'll probably do a majority or a plurality vote, which thing happened to be the most common. And you can do that to get one final set of predictions. If your goal is to do inference, I'm going to stick with linear models here because that's the most common type, the most common time that we're going to do inference. If your goal is to do inference, let's say I want to understand what is the relationship of age on income and sex on income. I want to know what that value of beta 1 is and that value of beta 2, and I want a confidence interval for it. Well, we can't just average those predictions in the same way because that doesn't make sense. But there are a set of rules that can be used to combine this information, and this is on a later slide, but there is a set of rules known as Rubens Rules. Rubin and Little are like the two godfathers, I guess, of missing data. And Rubens Rules has a set of rules for you to take your beta 1 coefficient on each of those 10 models, your beta 2 or your beta naught or whatever for each of those 10 models, and combine them together. Or if you get confidence intervals for each of those beta 1s, Rubens Rules will tell you how to combine those together. That will allow you to summarize the total uncertainty in your data based on what you know. And you do so without making up data at any one point. You at no point plug one value in for this NA. You instead are representing that NA with a distribution. which is kind of the clever trick about it. You're not actually making up data. And when my survey sampling professor walked us through missing data, I'm like, that's not true, because I feel like I'm missing or making up data. And I still sometimes feel like I'm making up data, but I know that we're not actually making up data at this point. So realistically, we're gonna make a lot of copies of our data set. We're gonna randomly simulate 10 values from whatever that distribution is that we get from, you know, making a prediction about sex or income or age or whatever we're trying to fix. Fill each copy in with one of those 10 values. We do our final model or our final analysis on each of those 10 data sets, and then we're going to combine those results together. For predictions, we're gonna average them or do a plurality vote, or if we're trying to do inference, we're gonna use Rubens rules to bring those confidence intervals together into one summary for those different coefficients. That is the intuition behind imputation, and that is what imputation actually practically is. So, to put it on a slide, for proper multiple stochastic regression imputation, you're going to come up with a data set. For each data set, you generate a set of coefficients for your regression model. Then for each missing value in each data set, you're going to replace each NA with a value predicted from a regression line or for some model that you've constructed there. You do your final analysis or generate your final predictions on each data set, and then you aggregate that analysis or aggregate those predictions over all 10 of those completed data sets. And these have been done by properly estimating the amount of variance in your data, because we properly estimated the amount of certainty or the amount of uncertainty we had in those values. And it's like what you were talking about earlier. Rather than just plugging in one value, this allows us to plug in a distribution of values and summarize our total understanding of what that value of NA could be. This is a very good version. This is a valid method of imputation. The downside, it's going to take more effort to implement. This is harder for us to just do from scratch. I've listed two packages here, Fancy Impute in Python and Mice in R do this. Mice stands for multiple imputation by chained equations. It's a specific implementation of this method. The other downside that is important to note, this assumes that your data are missing at random. This assumes that your data are missing at random. Now, frequently, from a practical point of view, people will say, look, we make assumptions all the time that should be met and probably aren't. Even if my data are missing not at random, I'm going to assume that it's missing at random so that I can use this method anyway. Practically, that's going to happen. People will still do this even if the data are missing not at random. However, it does make that assumption. So a perfect example. Earlier, we were looking at a value of sex that was missing. If somebody says, look, I don't identify with either male or female, given the data that I had, there'd be no way for me to predict that, because given the data I had, I'd not observed that particular value. That's a perfect example of data that's missing not at random. That data is missing because of the value of that variable itself. In that case, if somebody neither identifies as male nor female, we would not be able to make that prediction because we hadn't observed it. Similarly, let's say that instead of that, I was trying to predict income. Well, if the incomes that I were missing were all, lower incomes, this will now be compromised by that. This will now be making predictions from the people who had lower incomes or the people with higher incomes or whatever subpopulation I had sampled. So this does assume that your data are missing at random, which is not great. I wish that it wasn't the case, but that is the proper method of this imputation. Two comments about this imputation. One is...
Are you saying it's valid, or it's only valid if we know the distribution to be normal?
It is, so, it's a good question. So this is a valid method of imputation in that we are properly estimating the variance and the certainty in our data. However, it does rely on a number of assumptions. One assumption, probably the most difficult assumption, is that we're assuming that our data are missing at random. The other thing is that when you are replacing your NAs with like some regression model or any model, whether it's a random forest or linear regression, logistic regression, Poisson regression, whatever, we do assume all of the assumptions of those respective models, depending on which one you use. So if you're using a linear regression model to impute those values, you do assume that those errors should be normally distributed. If not, or if you feel that's not a good model, you should pick another model that better matches your assumptions. And so commonly, people might try and do something like a random forest where you aren't making any parametric assumptions about the distribution of that data. So this is not limited to, but has been most exhaustively studied in the context of using linear models to generate those predictions.
Right. But generally people they look at the shape of the distribution, they find whatever
Yes, I think you're overestimating the number of people who would do a Box-Cox transformation. I mean, I think
What was the phrase, Box-Cox?
Box-Cox transformation. Quick show of hands, how many people have used a Box-Cox transformation before? Yeah, I agree with you in that you should do that. So a Box-Cox transformation is an algorithmic way to identify the proper transformation of your data to essentially convert it to normality. So that normality assumption would be met if you were to fit a linear regression line to it.
But it's typically, it's almost always log 1 plus or log. So we know the distribution of ages is negative exponential, so we just take log 1 plus log 1. Now we have something that's sufficiently, maybe truncated below 14, and that's it.
Correct. Again, I think that in many cases, thinking about the practice of data science, there are a lot of people who aren't checking those assumptions and would apply this regardless. It does assume that those assumptions are met, but I would venture to say that many people, when fitting a linear regression model, don't check for normality of those residuals or of those errors, which is a whole separate discussion. But yes, under the hood, we are making that assumption that the regression model we use here was properly specified, and that our data are missing at random, which may or may not be true, and it's up to you to determine how much you're willing to actually make that assumption, or make those assumptions, I should say. So 2 comments about imputation. First, we did not make up data. We did not make up data. We did our analysis by estimating the amount of variability in that data, but we did not make up any data. We never replaced an NA with one specific value. We essentially replaced it with a range of values. We replaced it with a distribution that we could then say, all right, given this distribution, what are the different values it could take on, and how frequently would I expect to see those different values? However, and to your question earlier, you asked about, like, if you were doing this as part of EDA, for example. I think this somewhat connects with that.
What's EDA, please?
Exploratory data analysis. Sorry about that. Yeah, EDA is exploratory data analysis. If you're trying to do this as part of your exploratory data analysis, like do essentially data cleaning, and you want to fill in the missing values. If your goal is just to have a complete data set to be able to put into an analysis or pass on to someone else, be very careful about this, because after you construct that data set, after you do mean imputation or stochastic regression imputation or whatever it is that you do, nobody's going to be able to know what was real and what was imputed. And I recognize that that's frequently a problem that we have, or that we face, is that we just really want to fill in these missing values so that we can pass this data on to other people so they can then use that. But you want to be careful about that, because we are at that point effectively making up data and sharing that with people. So I don't know the right way to caveat that, but nobody's going to know that difference between observed and imputed data, so you just want to be cautious if that is your goal. I'm not saying that it is never going to be your goal to do that. In a perfect world, it wouldn't. But given that, this is something that that you should just be aware of. So, if your goal is inference, use Rubens Rules. I have a few links in the repo, as well as these links here, about if your goal was to fit your linear regression models on different data sets and then combine those beta 1 parameters later into one confidence interval or whatever, you can use Rubens Rules. Here are some links for that you can check out if you want to get into the nitty-gritty of how exactly you would do that. The last thing I want to do is called the pattern submodel approach. This is a very, very recently published method. This is something that was published last year in the summer. It is relatively, the benchmarks about it are quite good, but what we're going to do, big picture, is we're going to take our data set and we're going to break it out based on the pattern of missingness. And we're going to visually see what this means in a minute, and we're going to fit one model on each missingness pattern. So what I mean by that, I've got this data set here, I have my y values, I have x1, and I have x2. So 3 variables in my data set. For y, I've observed all of my data. For x1, I've observed the first 4 values and not the last 3. For x2, I've observed 4 values and I'm missing 3 of them as well. And what I'm going to do is I'm going to break this out into its missingness patterns. Basically, I'm going to take everything that's missing together and I'm going to put it into one group. So for example, here I have pattern 1. Pattern 1 corresponds to all of my observations where I have observed every value. Pattern 2 is going to be the next 2 rows in this case. I've got I've observed Y, I've observed X1, and I have not observed X2. I'm going to put those into its own pattern. I'm going to do the same with patterns 3 and 4 here. And then I can define what pattern each belongs to. So I might add a column to my data set that says pattern, just so I can see like what each pattern corresponds to. What I'm going to do now is I'm going to take my data and I'm going to split my data frame up into pattern 1, pattern 2, pattern 3, pattern 4, and however many patterns I have. And I'm going to break them into these different subsets, and I'm going to fit a different model on each of those subsets. So rather than doing any imputation at all, what I might do is I might say, let's just split our data up into these patterns, and I'm going to fit one linear regression model on the first pattern, one linear regression model on the second, one on the third, one on the fourth, and so on. And in doing so, what I'm able to now do is I'm able to have all of these different models. I no longer have one model, but I have a different model that is going to be fit to each different missingness pattern. I can do this without needing to make any assumptions about why my data is missing. So in this case, I don't even need to focus on what type of missingness I have. Let's say that for pattern 2, let's say that X2 is income. So income is missing for these people. I don't need to really care why these people did not respond to my question about income. Instead, I just need to say, oh, income's missing. I'm not even going to fit a model including income in it. I'm just going to fit a model Y equals beta naught plus beta 1 times X1, and that'll be it. So I fit one specific model to that pattern, and I'll fit a different model to this pattern where I've observed income and I haven't observed sex or whatever it is, and so on. So I'm taking my data, splitting it up into different chunks based on that missingness pattern, and it does not require any assumptions in terms of that missingness, and we can do this. I've got a little bit of pseudocode. This is not actually code that will.
Is there a name or a phrase for this?
Yes, it's called the pattern submodel method. Pattern submodel.
It doesn't have a name like Fred Flintstone's method.
It does not. No. The authors on the paper, one was from Harvard, or one was Mass Gen and Harvard, one was from Vanderbilt. I think one of the names was like Mercado, but this is like recent enough that I don't know people would call it Mercado's method. Because it was it was like July 2018 when this was published. So this is still very, very new. Yes?
I mean, essentially, it's mostly imputation. You're building a piecewise model in each sort of subpopulation according to where missing is going.
Well, we're not imputing at all. We're not actually going to be filling in any of those missing values.
Okay.
Yeah. So we're literally just fitting models on the data that exists.
Yeah.
And so we're at no point going to attempt to fill in any missing values.
Okay, so modeling again is, but I mean the point is you're doing it piecewise on each subpopulation.
Correct. That's exactly it. Yeah.
And
Okay.
sorry, like if a lot of those populations, if you have n columns, n is large, and if you have two missing, you're just going to get like a patchwork built up lots and lots of small models.
Technically, yes, but we'll talk about that. I'm addressing that in like 2 slides. Yeah.
I was going to ask how this is different from regression imputation, but you just said that it's not imputation.
Yeah, we're not actually filling in any missing values here, and which is a benefit of this. So when in looking at this, I'll go back to this slide. In this case, I'm never going to try and fill in any missing values here because I don't care. I don't care why things are missing. I don't care how things are missing. I don't care how many of those values are missing. I'm never going to try and fill them in. I'm never going to estimate a distribution for this because I recognize, if I try and fill in a distribution for these values of X2 here, that's assuming missing at random. That assumes that these are missing based on, other variables, or it's explained by other variables. But in this case, instead, I'm like, look, let's just fit a model to this specific subpattern that doesn't bring X2 in at all, like income. Instead, I'm just going to fit a model using this, and there's no imputation here whatsoever. So this is neither deductive imputation nor an inferential imputation approach. This is separate, and this is a non-imputation approach to handling missing data. And so if we look at like the pseudocode, we're just going to iterate through each of our patterns. We're going to instantiate a model and fit it only on the training set where that pattern is met, or we've got that particular missingness pattern. Then we're going to generate predictions, or we're going to do whatever analyses we want, and then we might score those models. But that's the extent of what we're going to do. We're just going to fit a different model on each of those subsets of our patterns. So the upsides to this, it outperforms imputation methods. Again, we're not imputing here. If your data are missing not at random, we're going to outperform imputation methods. It's also going to be on par with imputation methods for missing at random and missing completely at random. So, with missing at random and missing completely at random, it'll perform the same. But if your data are not missing at random, this method is going to be better, which is pretty good. It allows you to generate predictions for test observations with missing values. If you use an imputation method and you fill in these missing values, let's say now you get one new test observation that's missing some of those covariates that you have. If you're missing maybe x2 in that test value, now using the pattern submodel approach, you just pick the model that fits that missingness pattern. You don't even have to try and fill in that missing value for your test observation. You can handle test observations that happen to have missing values. You don't need to worry about it. Thinking about or comparing this to multiple imputation, where you're creating multiple copies of these data sets and simulating all these different random values, it's going to be computationally efficient. It tends to be a relatively intuitive method, and the best thing is that it doesn't require missingness assumptions. Doesn't matter if income is missing at random, not at random, completely at random, whatever. It is substantially better to do that. The downsides are related. One is it's a very new method. That means it's relatively untested. It's been peer-reviewed, it's been published, but we know that that's not always wonderful. And it's not a well-understood method for inference. So if your goal is to really conduct inference on beta naught and beta 1 and beta 2 in your final model, you should stick with multiple imputation and do those Rubens rules. You should not try and do this. Because in this case, this is not guaranteed to give you good inferential outputs, because you're fitting models on different subsets of your data, and there's all sorts of things that it just hasn't been thoroughly studied. So, to the point that Stephen had, if you have p predictors, it's possible to have up to 2 to the p different patterns of missingness, requiring you to build 2 to the p different models. In practice, your number of missingness patterns is likely to be far lower than that. In general, you will probably not have 2 to the p different values for that. But if you have a missingness pattern with a small number of observations, like you've got a missingness pattern that only has 3 observations in it, consider trying to collapse that into a broader category if you can. Because if you can collapse that into a larger category, then you're reducing the number of models you need to fit by 1, and you're able to increase the sample size of both this category and the category that it collapses into. Yeah?
So this might be where if you look at the correlation plot and begin with where earnings occur, and just look at the hotspots, so like,
Yeah.
age and something else, and then you can get a hypothesis, not a scientific hypothesis for what's correlated.
Yeah.
Generate your
Yeah, so I think that would be helpful as you want to look through these and figure out what are the patterns that you have, what are the different variables that you might try and collapse together, or where you might run into a situation where that is necessary. I have some text here. In the interest of time, I'm not going to go through this text, but this is a text in the slides that you can see if you are trying to, if you've got a few different groups with small numbers of observations, how might you consider collapsing them into broader categories? The last thing, practical recommendations. So as you practically tackle missing data, first, if you try and figure out what type of missingness you have, there's a couple of ways to try and go about this. First, there's something called Little's test for MCAR. So it's a hypothesis test that assumes that your data are missing completely at random, and then the alternative hypothesis would be that your data are missing at random. It's very similar to the student's t-test, or a multivariate version of that. The downside is that there's not an empirical test to evaluate not missing at random, so there's no way for us to tell whether our data are not missing at random, because that could really fall under either of those hypotheses. So if you say, I don't believe my data are not missing at random, but I want to compare these two, Little's test can help there, but otherwise won't detect data that are not missing at random, which is not great, but there's no empirical test possible to do that. Second, what you might do is partition your data into observed and unobserved data sets, then compare them. So let's say that I am looking at income, and I have my full data set. Income is observed for some of them, and income is not observed for some of them. Maybe what I'll do is I will take those two data sets and basically break them into two, where income is observed and not observed, and then I create a histogram for age, and I see, is age different among my observed group and my not observed group? By doing that, what I can do is then say, oh, I think income might be missing at random, conditional on age. I think age has something to do with whether or not that is missing. You could consider doing that by splitting your data where it's observed and unobserved, then compare summaries of that to try and say, can I identify whether or not variables that I've observed seem to have an impact or seem to be associated with missingness. If your data are missing completely at random, if you choose to check that out, you can use any of those methods that I previously discussed with their respective caveats. So for example, you can use stochastic regression imputation or hot deck or whatever, but these are still invalid methods of imputation. So what I mean by that is you're still underestimating your variance. Just because your data are missing completely at random doesn't fix that. However, if you say, look, I don't have time to do the pattern submodel approach or proper imputation, you could consider doing those. It still has those earlier caveats, but your results should be unbiased if you choose to do that.
Which one was proper?
Proper imputation was the one that we talked about at the end where we make the 10 copies. It's like the proper stochastic multiple regression imputation. We make 10 copies, put a distribution in for each of those NAs, and then randomly simulate values from those distributions. It was the one that we walked through after we walked through the intuition of what imputation should be. Yeah.
When you're going to actually do end months, if your bank right?
That would be for the pattern submodel approach, which is different from proper imputation. The pattern submodel method, you could have up to 2 to the p models if you have p variables. In practice, you generally don't realize that many different patterns of missingness. Proper imputation was where we made multiple copies of our data set, filled in a distribution for each of those. And then once we filled in a distribution for each of those, then we could simulate values from each of those distributions and aggregate our predictions or inferences across each of those data sets.
But we know it works if you know the underlying distribution.
You do assume, remember, for proper imputation, you are assuming that your data are missing at random. So you are assuming that your data are missing at random conditional on other things. Yeah. And so if your data are missing completely at random, that is like a subset of missing at random conditional on other things, which is not really conditional on anything. So you could still use these methods there. For missing at random, you could use these different models: deductive imputation, pattern submodel, proper imputation, stochastic regression imputation. This assumes that we include those missing at random variables in our model. So missing at random was where we had a sensor that went out from 6 a.m. to 10 a.m. I would have to include time in that model, otherwise this will be biased. In addition, complete case analysis will be biased, so you should not use complete case analysis. That is, you just take the data you have and assume that that data is sufficient. And then finally, if your data are not missing at random or missing not at random, you should use deductive imputation and the pattern submodel approach, and those are essentially it. Everything else should be biased, so you cannot or really should not use those methods. Because thinking about that, people will still commonly use those methods when the data are missing not at random. So the workflow that I have, first, is it worth my time? See how much missing data I have. Is it worth my time to fix it? Next, is it reasonable to attempt deductive imputation? Try and fill in missing values using logic where you can, before needing to go to inference. Next, if your goal is to generate predictions, the pattern submodel approach is going to be the one that you should use, because this has been shown to perform as well as proper imputation for missing completely at random and missing at random, but to be better for missing not at random, which is more common. So if your goal is to generate predictions, consider using the pattern submodel approach. If your goal is to conduct inference, what is the influence of one variable on another, or the relationship between them, then try and estimate what type of missingness you have for each variable. Use the best accounting for missingness method given the constraints that you have. Get as close to proper multiple imputation as you can. And then if you do proper multiple imputation, try and combine those results using Rubens Rules, which I've mentioned but did not explicitly go through what those are. That will allow you to combine your coefficients across models. Last slide, good, fast, cheap. Think about that. You have, the methods that you've likely been using are probably the fast and cheap methods. You fill in the mean and you move on with your day. That is fast, that is cheap, but it's not good. Think more broadly, can you pick a good and fast analysis? So can you spend your time up front and your money up front getting data that's complete, but then your analysis is easy because then you don't have to do any type of imputation or any type of accounting for missingness? Or can you do good and cheap analysis where you don't spend that time or invest that time up front in trying to get complete information, because maybe that does take too much time up front, But instead, what you can do is spend your time on doing like proper imputation, or you can do the pattern submodel approach if your goal is to do predictions. So think about what makes the most sense here in the context of the project that you need to do. I'm realistic. I know that there are time constraints that you all have. I know that you're not going to be able to just do the pattern submodel approach in all cases, but that is something to keep in mind. What is the best thing in the situation that you have? So with that, that is all that I've got for you. It is 12:49, so I imagine that, I know that 12:50 is our end, so I'm very happy to stick around and excuse me.
Could you say a few words how this does or does not apply or differ from data cleaning? Because clearly there's a lot that's common and things that are different.
So with data cleaning, well, really quickly, first off, I'm going to stick around for questions, but if you need to like leave, I know a couple of people have left, but if you need to grab lunch or coffee or whatever,
Two-thirds of the people
feel free to
data
do
cleaning
that.
2 orders of magnitude more than they do this class, semi-classical.
True, but yeah, that's going to be all data scientists. Is you're gonna spend more of your time cleaning than doing other stuff. With the cleaning or any type of exploratory data analysis you might do, the risk, or what I would encourage you to do, is only stick with deductive imputation, where you can deduce or purchase that value and you can fill it in with certainty or with near certainty. If you get into a situation where instead of that, you are dealing with because doing proper imputation, you're gonna come up with like 10 different copies of a data set, which I don't think you can. It would probably be difficult to like clean the data or to come up with these 10 complete copies and pass them along to somebody else who might not be a data scientist or who might not know as much, and get them to like do an analysis with all 10 of those. So as it relates to data cleaning, if your goal is to come up with one clean data set, the only thing that I would, like from a rigorous point of view, recommend that you do is deductive imputation, where you can logically fill in those values. But beyond that, I don't think that any of these methods would be appropriate for that.
It's equivalent to saying your default hypothesis in data cleaning is that the data is missing an element. There's some bias in here. It might be IP, it might be some data is collected, it might be how much of the surface techniques. Many of these methods go out the window if you know that the thing's empty. I was going to say, conversely, if you do a survey, there are methodologies about constructing a survey to make sure your sample is representative. So unless you really screw it up, your default assumption should be that the sample is fairly representative of what you're attempting to measure. It's like the start point is something. If you look at the average data set from e-commerce company, there's tons of garbage. They don't even have data for it. Even the time zone is wrong. You get people in Hong Kong logging in specific time zone. So it's like worlds of data.
So
Thank you.
yeah. What other questions do you have?